For this last session. This is the talk where we put together everything that you've learned in this whole 2 weeks into. Actually, I thought since your mind's already so packed, we'll just do a few small. I'm going to do 3 or 4 small topics. So if you lose me in the first 20 minutes, you can relax, and then I'll do something different in the next 20 minutes. So the first thing I want to do is talk about some.
Things are not linked.
No, not linked today. So the first thing I want to do is talk about some simple knot theory ideas where there's still quite a few elementary questions that are completely open. So I'll start with the stick number. Remember, we can think of a knot as being made out of a sequence of straight edges, so some embedding of a polygon into space. And the stick number is the minimal number of edges required to make that knot. So, for example, for the trefoil knot, it can be made with 6 segments. How many is that? One, two, three. Anyway, it's possible to make the trefoil with 6. Here, let me do it properly. There. So, just because I can draw it with 6 segments on the blackboard doesn't mean that you can actually realize it with 6 straight lines in 3 space. So I'll give you a little bit more information. I'll give you the heights of these vertices. These 3 will lie on the blackboard, and this one will be behind the blackboard, and this one will be above the blackboard. Okay, so now you can see that they interweave properly.
Is there anything that you can draw this way on the board which doesn't have the...
Oh, yeah.
Maybe?
Yes, I'll show you one in this. Okay, so Nati asked, is there really... So this is actually a big theory of line arrangements and so on. The interweaving is certainly does affect it. But let's ask the question. So we see here a knot with 6 segments. Is there a knot with 5 segments? Can you make any knot with 5 sticks?
So you mean the planar or the space?
In space. So this is not an open question. I'll show you the answer. So you might think of something like well, the answer is no. So let's see why. What about 4 sticks? With 4 sticks, we can only have 1 crossing, right, with 4 segments. So that's not enough to have a knot. Well, with 5 sticks, let's take one of the sticks and put it perpendicularly to the blackboard. Okay, so here it is. There's the 5th one. So now you see that you can't do it with 5 sticks either. Okay, so now we have a problem for the local people. Okay, there's a link with 2 components, which I've drawn it with 6 straight segments. How many segments do you need to make this in R3? What is the stick number of this link?
So now you're answering my question.
Yes, in particular. Okay, so first of all, you can't do it with, it's pretty clear you can't do it with 6, I think. How many can you do it with? We can do it.
Sticks are a little flexible.
Yeah, no flexible. So if we put a vertex in the middle of each of these, then we can go down and up and down and up, no problem. So it's smaller or equal to 9. 3 plus 6. But can we do it with 7 or 8? So somebody suggested 7? Okay, so I claim you cannot do it with 7, because if it was 7, then one of these would be a flat triangle, 3 and 4. So you could put that, you could look sideways from that triangle, put that triangle perpendicular to the board, and now you'll see that this actually crosses this, has to cross the plane of this triangle 3 times to get a linking number. So you'd see, and in fact it would be oriented. You'd have to have 3 segments crossing through that triangle in order to get the linking number of 3 that you have here. And so then you would need at least another 3 to connect these up. So you'd need 9 in total if one of them was a triangle. So that means you need at least 8. Perhaps 2 quadrilaterals could do it. And in fact, it is possible to make this with 2 quadrilaterals. So I'll give you Chaim's solution, which he, let's see if I can draw it. So this is one of them. It's almost in a plane. This is one of the 2 components here. And the second component looks like it goes through here and then back out through here. And then around the back. So they both look like fairly flat quadrilaterals. One is tilted a little relative to the other.
Intersection that you specified.
Which one?
The next one?
This one?
Yeah.
That goes over, right.
So that's a realization of the knot, but not the diagonal.
Right. So that knot can be realized with 8 sticks. Okay, now let me give you a couple of open problems in this area. This is of some interest to chemists because when you form chemical bonds, you take atoms and they have fairly rigid bonds when atoms are combined to form these polymers, in particular these biomolecules. And so you can think of these edges as being these chemical bonds, and then when you form a closed molecule, which chemists can do, then you can get very different chemical properties if it's knotted compared to when it's not knotted. So for experimental chemistry, when they try to create these biological molecules, they're quite interested in trying to create various knots. Okay, so let's look at open problem number 1. So this is if you take the 2n torus knot, which is a very simple knot, it just that might have been, yeah, that's an example. So you can take n crossings this way. N would be odd in order to make it a knot. And you can ask, what is the stick number? That's an open problem for this class of knots. How many sticks do you need to make such a thing? The conjecture is n plus 3. So for the trefoil knot, for example, is the 2, 3. This is the 2n torus knot. The trefoil is the 2, 3 torus knot, and for that we needed 6 sticks. So the conjecture is that n plus 3 will do in general.
Does it have any connection to other clusters in mind?
Not really, no. That's one of the reasons. It doesn't have a natural connection to.
Not even a bounds or something?
Well, there's some bounds, some trivial ones like crossing numbers and so on. But
Such realization is known. Do you know? I mean,
There's an upper bound, known upper.
Yeah.
This n plus 3 a known upper bound.
that's a good question. I'm not 100% sure what the answer. Yeah, that's right. Yeah, so probably, but I'm not 100% sure. No. Well, there's some lower bound coming from the fact that any two edges can only cross once, so you'll get something like square root of n, out of there. And another interesting question that's unknown. This is not a mainstream invariant. This is not something that's been looked at a lot, but I just thought it'd be fun to show you something that's easy to understand and which easy to understand the definition, but which very little is known. So another open problem, is the stick number of a knot equal to the equilateral stick number? So this is the same thing, but all the edges are required to be the same length. So amazingly enough, it's not known whether that restricts what you can get. Most likely, no. Right. Okay. So that was sort of just for interest, a warm-up topic. So now I want to describe something called virtual knots, which have been studied in recent years, introduced and studied, and try and say something about them. So this comes up when you try to create some kind of code to describe knots. So let's look at an example of a knot. And take the figure 8 knot. What did I do here? Did I get this wrong? Yeah, I did. Over and under. Okay, better. So this is the figure 8 knot. And I want to create some kind of code to describe this. Say I want to do some software analysis of knots. So Gauss came up with such a code. It's called the Gauss code. And it goes like this. First you pick a base point. It's Gauss. So it goes like this. You first pick a base point, and now I'm going to number all the crossings. I'll orient the knot, and I'll number all the crossings as I go around. So it doesn't really matter so much how you order them, but let's order them like this, 1, 2, 3, 4. And I'll describe what I see as I walk around the knot starting at this base point. So the first thing I see, let me draw the orientation in a few more places. Oops, what did I do? There you go. So the first thing you see is you get to crossing number 1, and you go over crossing number 1. So you go over 1, and what's the sign of this? The sign of this crossing is a minus. In fact, let me put in the other crossing signs. This one is a plus, this one is a plus, and this one's a minus. So these are oriented knots, so every crossing has a sign, depending whether it's right-handed or left-handed. So we say we go over 1, and 1 is a minus crossing. And then what do we do next? We go under 2, and 2 is a plus crossing. So we just keep indicating like this what we do. We go over the crossing number 3, and it's a plus crossing. And then we go, what do we do then? Then we get under crossing number 1, which is a minus crossing, and then under 4, over 4, which is a minus crossing, under 3, which is a plus crossing, and then over 2, which is a plus crossing, and then under 4, and now we're back where we started. So there's some redundancy here, right? We didn't have to put the signs twice, and so on. That's okay. There's a little bit of redundancy in this description. But now we have a sort of a series of symbols. Every number appears twice, once with an over and once with an under. And just describe... Where? Over here? Or where did I say that? Well, we went under 4. 4 is a minus crossing. So we just indicate that. It's redundant to indicate that twice, but we're not so worried about storage. In those days, there wasn't an issue. Okay, so let me give you an example of such a code, and you draw the knot for me. Let me do it for this knot, okay, and then I'll give you an example. So supposing we only had these set of symbols, how would we draw the knot? Well, we start at our base point, and this tells us the first thing we're going to do is go over. So we're going to go over something. We'll call that number 1. And the sign of the crossing is a negative, so that says that the orientation is down here. And then we go under 2. So the next thing, number 2 will go under. And it's a plus. So that means it goes down as well.
No, it goes up.
No, it's down because you put your thumb on
We
it.
are under, sir.
And then we'll go over 3 with a plus. So plus looks like this. And then under 1. Okay, now we see 1 for the second time. So I don't want to draw 1 again. So I have to go under 1, and I already know which direction I need to go to. Because so I go like this. And if you think about it, I have really no choice about how to connect up. That's not quite true. I could slide over infinity. I could have gone like this. But if you think of doing this on the 2 sphere instead of on R2, then you see that we have no choice at all about how to proceed. So what do we do then? We just did under 1. Now let's go. Now it says go over 4. We don't have a 4 yet, so we have to make a new crossing that we go over. We'll call it number 4. And it's a negative, so that means it goes this way. And then our next thing to do is go under 3, so we have to connect up to 3 here. No choices. And then over 2. and then under 4. And now we've visited everything, so we close up. So that is the figure 8 knot. We've reconstructed it. All right, let me give you an exercise. Reconstruct a knot. I'll give you the code. So this is a 5-crossing knot. So see if you can reconstruct it. Yeah, you don't want to do it now? Should we do it? Why not? So what do we do? The first thing we do is go under 1, and it's a minus, so it goes like this. I did that on purpose. Under 1, and that means it has to go the other way, right? And then under 2, going the other way, plus. It's a minus, so I think that's right. Yeah. This is a minus, right? U1 minus and then U2 plus. So this is 1, 2, and then U3 minus, and then O4 minus. And then U5 minus, minus. Okay, now we just start to connect up. So the first thing we do is go over 1, so we go like this. And then over 2. And then over 3, and then under 4, and then over 5, and then we close up. Okay, so you see there's a couple of canceling crossings there, but this is a trefoil knot. So it turns out that every diagram can be described this way. And there's a nice way of organizing this information, which is we can draw a circle, and we'll put the base point at the top. So we'll label these points 1, 2, 3, 4, 5. And then we see 1, and so we see that as we go around the circle, 1 is now connected up to 1. And we indicate which one is, the first one was the undercrossing, and the second one was the overcrossing. So we put an arrow pointing from the over 1 to the under 1. Okay, so but by means of these arrows, we can keep track of which is the overcrossing and which is the undercrossing. And we also put a sign, a plus or minus, along each one of these arrows. And this is called a Gauss diagram, what I'm drawing now. It's a circle with some chords in it. We'll continue. There's a 2 here. So we went from an under 2 to an over 2, so the arrow goes like this. And again, the sign is a plus this time. And we went to an over 3, an under 4, and over 5. So we connect the two points corresponding to the same crossing. We put an arrow pointing to the towards the under from the over. And we put the appropriate signs on each one as well. So from this information, we can reconstruct the 3 was a minus. From this information, we can reconstruct the diagram. In fact, we don't need these numbers anymore once we have the arrows and the sign. So this is called a Gauss diagram and corresponds to a Gauss code. And as you saw with the finite type invariants, these are the objects that go into the computation of finite type invariants. So they started to be studied quite intensively when this theory developed. And then people found that there was an issue when you had things like this. So let me give you one more example. This one's very short. So it's only got 2 crossings. But let's see what happens when we try and take this Gauss code. This, by the way, looks like this. If we drew it as a Gauss diagram, it would look like this. What happens when we try to draw this one? Well, we go over the first with a plus. So that's 1. And we go under the second with a plus, like this. And now we have to go under the 1, so we connect up here. And then over the 2. And now we want to close up. So now we're in trouble. So this Gauss diagram is not realizable. So what we saw is that every diagram, so every diagram gives us a Gauss code. But it doesn't give us all the Gauss codes. There are more Gauss codes. Some of the Gauss codes cannot be realized, do not come from diagrams, like this one. So what do we do? How do we make this into a diagram? Well, the idea that was due to, about 15 years ago, due to Kaufman and Gusarov, Polyak, and Vero, was to create a new kind of crossing. So far we have 2 kinds of crossings, over crossings and under crossings. So we'll create a new kind of crossing called a virtual crossing, which you draw like this. So we'll call that a virtual crossing. So you have to pretend that that's not there. That's the breakthrough. Okay, so you ignore the crossings that when you create the Gauss diagram. Yeah. Yeah. So when you create a Gauss diagram from such a picture, you count these crossings, but you just ignore these. They're not really there, so that's why they're called virtual. And then you get a one-to-one correspondence between diagrams and Gauss codes. Yeah.
Could it be like a real crossing, then a virtual, then real, then virtual?
Yeah. Yeah, you could have many virtuals.
That would have a Gauss code as well?
Yeah, I think so. And then you can, so now you've defined these, now you've defined this space of Gauss diagrams, which is bigger than the space of real diagrams. It also includes these diagrams with virtual crossings. So, yeah.
If you're stuck in trying to close up your picture, is there some canonical way to?
Yeah, that's a good question.
Why do you need the diagram at all? The codes are
Yeah,
sufficient. Why
that's
do you need
right.
the diagram?
Well, you don't need the diagram is the answer, but you can encode you can make a correspondence between some new diagram and the codes, and now we can right. So I'll come back to that in a minute. the diagrams are only a convenience, just like ordinary knot diagrams. We could have just talked about polygons in R3. The diagrams are just a way to help us think about them, really. They're not really what the underlying knot is encoding, is describing. But they're a way of helping you think about it. So now let's think about Reidemeister moves and what happens to Gauss codes when you do Reidemeister moves. Supposing we're interested not in diagrams and their codes, but in knots. Well, so we know that knots are equivalence classes of diagrams, and we can ask what happens to the Gauss code when we do something like one of these Reidemeister moves. So let's think of it in terms of this Gauss diagram. This is maybe the kth crossing in our ordered list of crossings, and the Gauss diagram changes in a certain way. Namely, we have two adjacent points here, both labeled k. In this case, you'd go over k. K is a negative, and then you'd go under k. So the arrow would point this way, and you'd see a minus sign. And here, this chord in the Gauss diagram has just been removed. Okay, so this is a equivalence on Gauss diagrams. We're not really interested, if we want to study knots, we're not really interested in these diagrams. We're interested in the modulo equivalence. So I could, if I wanted, just add something like this. And that would correspond to somewhere on this picture putting in one of these things. So I'm interested in equivalence classes of Gauss diagrams generated by three kinds of moves. This kind of move corresponding to the first type of Reidemeister move. Let's look at the second type. When we do something like this, okay, well we can do that. So the question is, what if you had the other kind of type 1 Reidemeister move? Say, let's do that here. Say it looked like this instead. So this time it's a plus instead of a minus here.
Two consecutive cases.
It would still be two consecutive things. This time the arrow would point the opposite way because you get to the underside. What's that? Oh, I see. No, if the arrow pointed the other, I mean, there's also the two possibilities about which way you're coming to this point. You might come from the left or the right, and you might be over and under. So there's four possibilities altogether. I think all the arrows are allowed for this case. For the type 2 Reidemeister moves, there's another kind of move on the Gauss diagrams. So let's see if we can think what that is. So this is the move that say takes this to this. And let's put arrows on. So there'll be a few variations depending on which way the arrows go. Now there's also another question that will come into here. This corresponds to some Gauss diagram. And in order to see what it looks like, we have to think about how these guys connect. So this guy goes out here, and with this orientation, we know where it comes back. Right? This is a single knot, so this is eventually going to come in over here. Right? It can't connect over here because then the orientation would be backwards. So it must come back here somehow. So by picking the orientations, I have also said how these arcs connect to one another. So let's say we started here and we call this k and this k plus 1. That's the order in which we visit them. So we go around here and we get to k and then k plus 1. So we're going over k And what's the sign here? It's a negative sign. And then we go over k plus 1. And it's a negative sign here, positive sign here, a negative sign here. And then we'll go around, and eventually we'll come back to k again, somewhat later. And we'll go under k with a minus sign. And then we'll go under k plus 1 with a plus sign. So the Gauss diagram here will be, you'll go from over k to under k, so there'll be an arrow like this, and there'll be a minus sign here. And then this one will go like this with a plus sign. And one of our rules is going to be when we see two adjacent, there's nothing in between here and here. When we see two adjacent arrows like this, we're allowed to remove them. So here you just see the empty set on these two intervals. We've removed these two. So that's going to be one of our moves. And there'll be a different one if the orientations go the opposite way. So you can also get some moves for Reidemeister 3. So you get this equivalence class of Gauss diagrams under the rules that you can either add a pair of arrows like this or remove them, or similarly add an isolated one like this. And the equivalence class of Gauss diagrams under these moves is called the class of virtual knots. So a virtual knot is a Gauss diagram equivalence class, and it's equivalent under these three Reidemeister move on Gauss diagrams. So it turns out that when you look at the equivalence classes, it might be that you start with a knot k. It gives you a Gauss diagram. And now you do some of these equivalences. Maybe you do some R1s and get another Gauss diagram. And then you do some other Reidemeister move on this Gauss diagram. And suddenly you're at a Gauss diagram which is not realizable anymore. It's only, so you started with a real knot, but this equivalence class doesn't keep you in the space of real knots. It could put you in the class of virtual knots. But the theorem proved by the theorem that was proved by Gusarov, Polyak, and Vero is that if you keep going, so this one may be not realizable, but if you keep going and eventually get some knot which is realizable, so you wind up with a Gauss diagram of something that is realizable, then these two knots are the same. So you don't, even though you leave the class of realizable knots when you do this equivalence, once you return to the realizable class, you're only in one knot, one class of knots. So this is a valid, in other words, this is a valid way to get invariance of classical knots. If you can look at these diagrams, which are purely combinatorial objects, just these.
Just understand, so every equivalence class contains at most or exactly one?
At most one knot
There are
class.
classes which are completely virtual.
Yeah, I believe that's true. Yeah.
I must say, I still don't understand how is it possible to realize all these steps via varied Reidemeister? How
No.
do we
Well, I didn't show you all of them, but it's not. You can leave.
Say if they take such two which are not where they're separated. You can add something like this, two things that you can't reach each other, but virtually you just formally you're
So you say that if you can bypass all these you just go from K to K1, you can bypass the sequence using only actual nodes.
Right. So Reidemeister's theorem says that some different set of moves that goes through realizable knots
Avoid,
that would avoid these. But you might have, you might,
Take longer.
yeah, that's right. But well, it could take longer. But it also could have been that you could find some of these moves that connect things even where there's no Reidemeister moves. But this theorem says that that doesn't happen. So that means that if, for example, if you define invariance on this bigger class of objects, then it restricts to an invariant of a knot. Well, these virtual knots have been extensively studied now. They've now generated all kinds of algebraic objects of their own. I don't want to say too much more about them. There is a theory, your question about why you want to look at diagrams. So it's hard sometimes to work with these diagrams. Say you want to get from one set of pictures to another. It's not so obvious sometimes how to pick these guys to move from one to the other. So you can work with virtual Reidemeister moves. So just like there's Reidemeister moves for combination for all real crossings, in this virtual theory you're allowed to make moves like this is a real crossing, so this looks like this. So in this virtual theory you're allowed to do things like move a pair of virtual crossings across another crossing, but you're not allowed, this is allowed, but here's something you're not allowed to do. You're not allowed to do okay, so not all. So it turns out that these moves that I showed you allow you to do things like this when you do the diagram. They don't allow you to do this. It's not so clear. It wasn't at all clear originally why that was true. Later it was discovered that this theory of virtual knots is completely equivalent to taking diagrams on surfaces. So instead of on the plane, you can take a plane with some handles added to it, and then these virtual crossings become things like this. Okay, so that becomes a virtual crossing. But that corresponds not completely trivial, but it is another way to organize that. Okay, so that's all I wanted to say about virtual knots. Yes, question?
If you do a virtual Reidemeister move between realizable Gauss diagrams, could you realize the actual move? You do Reidemeister moves between realizable Gauss diagrams.
Yes.
The actual move is realizable, like it's actually real Reidemeister move.
Well, I mean, there's a different sequence that's real.
Yeah, but it doesn't mean that if you get one move from realizable to realizable, it doesn't have to be a realizable move.
Yeah, that's right. That's right. A particular move may take you into the unrealizable space.
So, has this been attempted as a method to make the equivalence between knots more efficient?
I don't know anything in that direction.
Is there any new invariant of virtual knots that gives new invariant for knots?
Well, Right. So any invariant of knots will give an invariant of virtual knots. Or is it the other way around? Which way is it? One way is true. But are there new ones? New ones that came out of this theory? Not that I know off the top of my head. Right.
Finite type invariance generalized with n plus.
Yes, that's right. So finite type invariants, because they're defined in terms of these chord diagrams, in terms of these Gauss diagrams, they're very naturally defined on this larger class of objects. Okay, so the next question I want to ask is, what does a typical knot look like? So in order to make sense of this, you need to have, this is a new topic, so you need to have some idea of some distribution over the space of knots, or some notion of what a random knot is. So generally, historically, the kind of things that people have done is they've either looked at knots with a small number of crossings, or they've looked at special classes of knots, like we looked at alternating knots. And I think I mentioned torus knots. Oh, let me, so Abby told me there's one thing I have to do, which is, when your friends ask you about knot theory, you have to be able to at least draw one knot. You have to draw some interesting knots so that, you can impress them. So let me show you how to draw a torus knot. How to draw a complicated torus knot. So let's say we want to draw a 5-2 torus knot. So you draw two circles, one inside the other, and then you take 5 equally spaced points around the outside. And then you connect the points, connect each point on the outside to the next one on the inside, and then each point on the inside in the back to the one on the outside. Okay, so there's a 5-2 torus knot. Okay, so she'll be, it's on video, so I don't have to, she'll be checking. All right. Okay, so these torus knots have been studied extensively, alternating knots, but we don't know how typical those are. If we have some, for example, in human DNA, we have a piece of line. The scale of the DNA is like having a rope that's several kilometers long that's been stuffed into a ball, a basketball, and if you want to know how badly knotted that is, if it was randomly packed, then the typical examples we have don't tell us so much. So we want to know what's the behavior of random knots, and there's actually very little known. So there's several models. Hai mentioned some of these models for these random knots. So for example, one natural model involves, starting at a point and then taking a step of Gaussian length in a random direction, and then taking another step of Gaussian length in some random dimension. And after a certain number of steps, you just close up. So very little is known about such models, what's the distribution of knots in them and so on. It's easy to do numerical studies, but it's very hard to actually prove things in such models. There is one thing we know, in 2 or 3 of these models, which is the probability. So one thing we do know, and this was proven by Pippinger, Summers, and Zhao, that we do know that the probability that a random knot is unknotted goes to 0 with the number of steps. As the number of steps goes to infinity, the probability goes to 0 exponentially fast. So I'm going to look at a different model in a second, but just what's the intuition? This is not so easy to prove, but what's the intuition for it? Well, you take a few steps, and there's every time you take a certain number of steps, there's some probability that you'll create a little knot. Some non-zero probability when you take, say you take 10 steps at random, there's some non-trivial probability that you create something that looks like this, that's knotted if you say complete it by coming out perpendicularly from the blackboard. And then the probability that this will be canceled, that this knot will be canceled in the future as you keep walking is very small. In order for this knot to get undone later, you'd have to walk backwards and sort of retrace some of your steps. And by analyzing that kind of reasoning, you can show that it's pretty unlikely that these things will cancel, and so you'll get more and more of them as you take more and more steps. So probability of the unknot goes to 0. Let's look at a slightly different model, which is quite natural, but we don't know quite what the answer is.
Is it known in these models that with probability tending to 1 it's a connected sum?
I believe that's their argument, yeah. Yeah, that's the only way they know to show it gets knotted. Certainly that's the argument in the lattice case. Connect sum of a trefoil with yeah, they just concentrate on one knot type. A non-trivial connect sum in particular, yeah. So let's look at a slightly different problem. Supposing we take a random diagram with C crossings. So here's a diagram with 3 crossings. This gives 2 to the C knots. Each one of the crossings can be changed to an overcrossing and undercrossing independently. We can ask what proportion of these is unknotted. So let's look at some examples, and then I'll ask a question that we don't know the answer to. So let's take an example that looks like this. So what proportion of the crossing changes, we can change some crossings at random, say. What proportion of these, so there's 2 to the C of these, C crossings. How many are unknotted? All of them, right? You can't create a knot with such a big diagram. So sometimes they're all unknotted. Let's try another example. So this is a little combinatorics to count this one. This is the 2n torus knot we looked at before.
He's watching.
Okay, so we have C crossings. This is a 2n, oops, uh-oh, a 2n torus knot, which had, well, you can call it a 2c torus knot. It has C crossings. So if we look at the 2 to the c different choices of changing this crossing, how many of them are unknotted? In this case, this is these are all negative signs, the way I've drawn it here. So in general, if you change a crossing, you'll change its sign from plus to minus. So each one of these corresponds to some sequence of pluses and minuses. And when will they be? When will this be an unknot? You can cancel any two adjacent ones, right? So it's just something about the sum of the signs. Because if you have two that change sign, you get a picture like this. You can just cancel them. So if the sum of the signs is equal to plus or minus 1, then it's an unknot. So how many, out of these 2 to the c, how many of them have, how many, that's right, finally some combinatorics. Right? Okay, so for those of us who aren't as fast as that, it would be, you'd have to choose, out of these c, you'd have to choose c, how many are unknots? Well, if roughly half of them, if c over 2 plus 1, c plus 1 over 2, or c minus 1 over 2 are plus, then that would imply that, so you have to take c, choose c plus 1 over 2, which is about, what is it? About 2 to the c over root c.
I should have said c root c, but it's other c is a constant.
Right. Times some constant or something. So still quite a lot of them are unknotted. Can we find some diagram where there aren't very many? Where there's very few unknots. So let's make a question now. So for all diagrams with C crossings, let's let the u min of C be the minimal number among all C crossing diagrams of the number of unknots. So open is to find some find u min, or find some good bounds on u min. For example, is u min of C bigger than 1/2 to the c? We don't know that. Right. So what's the right way of saying that? Yeah, that would be the proportion. So how do I want to say this? So the way I've described it here is it greater than
Say 1.1 to the C.
okay.
No idea if it's this.
No, that it diverges.
Yeah, let me give you an example. I'll show you the best we know. The best construction we know is something like this. You take a trefoil knot, and then you take another trefoil knot, and then you take another trefoil knot. So you just take a connect sum of a collection of trefoil knots. So for a trefoil knot, it turns out that there's 2 ways to get a non-trivial knot out of the 8. So the number of unknots, if you count, is there's well, we can count unknots or knots. The number of unknots will be 6 out of the 8 choices here will give you unknots. So first observation is for this whole thing to be an unknot, each one of these summons has to be an unknot. Otherwise, you have a non-trivial connect sum. So you get 6, 8 to the C over 3 is the number of unknots. Which is roughly this is the number of unknowns over 2 to the C.
Yeah, so here you just proved a better theorem. This third root of 6 is bigger than
Okay, so what should I put here now? Right. So that's a good that's a good point. Yeah. Okay. Formulate your own conjecture about these things. We really don't know what the right answer should be. But how do you know that there's? If I give you some diagram, how do you know that there's any unknot? Is there always some choice of these 2 to C crossings that give me an unknot? Okay, and how do you get it?
Starting find the first time you get that. And let all these things above the other.
Okay, yeah. So what you can more or less what I was thinking. So you can start with some base point and just always go downhill as you go around. So I'll redraw it here. This is actually the easiest way to draw something because you never have to worry about getting the crossing wrong. You always go downhill. Well, always until you get back to the base point. Now you've gone way down, so now you have to take a jump up again over here. Okay, so why is that unknotted? What? Yeah, that's true. You could use an induction argument with itemized moves. That's another way to do it is to look sideways. Make this point that you picked here the z-axis, and let's think what we did. Well, let's put this z-axis. Let's just put it out here to the side. Then what happens? We started going down and down and down and down. And we always stayed on the left, right? Because we started on the ground. We went down and down, and then came back and went all the way up. So you can see that the projection in the zx direction has no crossings. It's strictly descending. All right.
Just to get this question formulated as well, so for every, let me use n.
Okay.
For every n crossing diagram, we speak about the number of ways to unknot it. You just showed us that this number is always at least one. And you show we ask what is the least number, and you also gave us an example where it's only 6 to the 1/3 to the n.
So we can talk about it as a function of the diagram instead of the crossing number, right? And
The
then,
number of ways to unknot the diagram.
right. So never of knots with
It's
that
always positive,
with
it's at
that
least
diagram,
one.
with that really the same projection.
Right. So you showed us two things, that it's always positive, at least one.
Right.
That's the picture to your left. And you showed an example. There exists.
We can make this 2,
Yeah.
not 2n. You
so
think-
You showed us that it's least
Let me
one,
just-
two.
Not 2n because you're thinking that it doesn't matter that if you start in a different place you'll get a different one.
Up and down.
You could go up.
You go up and down, that gives you 2.
Yeah.
But you can also try and start in a different place and descend, but that doesn't necessarily give you a different diagram.
Anyway, so we know
Yeah.
that it's at least 2,
Right.
and we know an example where it's only 6 to the 3rd to the n. There exist these for which that's the first one is for all b, and the
Yeah.
second one.
Right.
The second one is there exists a b
Right.
for which this is only 6 to the 1/3 to the n. Yeah, it is. You know the number. To the n. And you ask, can you go lower? So what is the least? How small can u of d be if d is a does it go to infinity? You can ask any questions that you want. But just what is the minimum of u of d for d and then crossing the
It's interesting to ask about the diagram and also about the average unlocking number, maximal unlocking number.
Right. Well, the maximal we know. We know some diagrams always give you unknots.
The first example that you drew,
No. Take the word. Well, okay, no, but that's the other way. You want to get diagram with maximum unlocking.
Oh, unknotting number. So a knot which has which contains a knot which has maximal unknotting number among all projections. Yeah, there's many questions of this type. So I have a couple of other things I could say. Let me just tell you a couple of interesting facts to finish. First of all, one thing that's...
So nothing better than this 2 is known.
What's that?
Nothing better than 2 is known.
Well, I suspect you could push it up a little bit. Yeah.
So 3?
Yeah, probably.
Can we make
I think you could make it 3.
it is
I
only
see.
divergence.
Hmm?
It is only being made divergence.
If you go to infinity,
All right. But yeah, I don't think we know anything more than what we have here. Yeah. So one thing that that I didn't tell you about knots, but which is sort of central to the theory, is that there is an algorithm to tell whether 2 knots are the same. So if you're given 2 diagrams of a knot, there is an algorithm which in presumably now doubly exponential time will tell you whether the 2 knots are the same. And so
Gauss diagram, so what diagram?
these are just, well, in this complexity, well, in the algorithmic setting, you can be given a diagram. You can be given K as a diagram or as a collection of edges in some simplicial complex. They're all equivalent in that you can get from one to the other. So from the algorithmic point of view, it doesn't matter that much. So you're given say two diagrams, and you're asked, do they represent the same knot or different knots? And that is algorithmically solvable. That was actually a very interesting history, that problem. It was asked by Dane around 1920. Dane formulated this problem, and it was one of the very earliest algorithmic problems of any type that were formed. So he asked for a step-by-step procedure where you take as input 2 diagrams and decide whether they represent the same knot. And Dane was a topologist and group theorist, and he, using some topology, what's now known as Dane's lemma, showed that this problem of telling whether two knots are the same is more or less the same as the problem of telling whether the 2 fundamental groups are the same. And he worked out ways of... This isn't strictly correct, but it is true certainly for the trivial knot. Anyway, so he formulated this as an isomorphism problem for groups. And he couldn't solve that problem. It turned out later, it was discovered in the 50s, that this problem in general is an undecidable problem. So you cannot solve this. Yeah, for general groups, it's an undecidable problem. Later, well, because there is an algorithm, it is decidable for the groups of knots. But the way he formulated it, it was, in great generality, it was undecidable. So the point is, though, that he formulated these problems, the isomorphism problems, the word problem, the conjugacy problem, for the first time while thinking about this knot isomorphism problem. So this was a fundamental problem in the history of algorithms. This was also an interesting story. Dane's lemma was really one of the fundamental basic tools used in all three-dimensional topology to study three-dimensional manifolds. And Dane gave a very beautiful argument, created lots of new ideas, but there was a fundamental mistake in his argument, which was so this was maybe in the 1915 or so, 1920. It was fixed in 1957 by Papakyriakopoulos. Who was a topologist at Princeton. And despite the fact that this was incorrect, it was so useful that people wrote papers in the meantime saying, assuming Dane's lemma, we can show this. And then later was shown to be true, so that was not such a foolish idea. The proof of these algorithms, the construction of these algorithms, is rather different in spirit from the kind of things we've been doing. It really uses, if you want to show that two knots are the same, the way these algorithms go is you really study the behavior of the complement of the knots. So you look at a triangulation of S3 minus the knot, and you actually do some complicated arguments to create a homeomorphism from one knot complement to another. So it really diverts into three-manifold topology. These algorithms were thought to be very intractable. I should say the algorithm was given by Haken around 1960. The same Haken who proved the four-color conjecture also was the first one to give an algorithm to show that this is a decidable problem. You can. Yeah, that's true. Later people found some gaps and filled them in. Is that what you mean?
It still requires the conjugacy problem for the method test.
Right.
This was done by Henry.
Yeah. Well, Haken certainly claimed it, and he had most of the ideas. There were other ingredients that were filled in later in the 60s. Even more recently, some gaps were filled. But the basic idea was given then, and it was thought to be intractable. But in fact, it now looks quite likely like that these algorithms may be just as practical as computing the invariance we saw during this previous discussion. It may be that running this algorithm is just as efficient as computing the Jones polynomial. So it may be that all these other invariants somehow become irrelevant if we can just algorithmically understand how two manifolds look. Yeah.
This is an approach using the Rademacher, by using two knots, which, as you say,
Yeah.
any bound on short is fast.
Yeah, that's a good question. That's an excellent problem. In fact, if you want to ask, is K unknotted, there was a bound, the number of Reidemeister, if you start with a C crossing projection, then you may have to go up to much more crossings on the way down. But there is a bound here, which was actually given in a paper that I wrote with Jeff Ligarius. And the bound we got was, we got the first bound, but it was based on Haken's work. It wasn't really a way of bypassing it. We just analyzed what he did and got a bound that way. So it didn't give a new algorithm. And the bound we got was something like, well, it was some constant to the C, so it was exponential in the number of initial crossings. But this was a very big constant. It was, I don't know, 2 to the 10 to the 11th or something like that. But singly exponential. Later, this has been very recently improved. So instead of K to the C, we now have a C to the 11th, polynomial bound. Then the algorithm would be, I think, exponential, that's right. Because the maximal number of moves you have to explore is polynomial. Not exponential, but the exponent would be a polynomial of some sort, maybe.
Is there a lower bound on how many moves you have to do?
So known examples, I don't know any examples of two knots where you have to do more than a linear number to get from one to the other. Oh, wait a minute. Did we? Quadratic number.
It's a paper of you.
Yeah, that's right. He and I have, Tom and I have a paper where we have, I meant to say quadratic, yeah. So we have a paper, I don't know if I could draw this, I won't try and draw it, but there is a knot with C crossings, an unknot with C crossing, where you need to, well, the number of Reidemeister moves, the number of Reidemeister moves you need goes, is you need greater than some constant times C squared moves to get it to the trivial case. But there's another question, which is how complicated the intermediate diagrams are. And I don't know any examples where it has to get more than linearly many crossings on the way from here to here. The number, although that's not known to be true. So this algorithmic aspect potentially could, make all these invariants a lot less interesting. There is now software being written. In particular, there's a group in Queensland, Australia, that has quite good software that in practice can take knots with hundreds of crossings and determine whether they're the same or not. So using ideas based on this. So these algorithmic methods are making a lot of progress. But I think the real interest in the invariants is not that they can be used to tell knots apart, but that they're revealing something about the geometry of space, which we don't quite understand yet. That's really what's appealing about them. Well, I think I'm going to finish. Thank you.